Steinhauer here, welcome back. Continue our discussion of HR diagrams and their importance in astronomy and understanding stars and stellar evolution. It's now time to figure out what these main sequence stars are, right? We know that 90% of the stars in the universe line up in this sequence from hot and luminous to cool and very dim. And we know the sun is in this group of stars. And so what are these stars? Well, they're stars like the sun. The main sequence stars are those that are burning hydrogen into helium in their cores as the main source of their energy. And so more luminous main sequence stars are very hot, and less luminous main sequence stars are very cool. What leads to that difference? Why are some main sequence stars much hotter and more luminous than others? It has to do with their mass. The main sequence is a mass sequence. How do we know this? Again, well, we've measured the masses of stars in binary systems that happen to be main sequence stars, and we find that the further up the main sequence you go, the higher the mass of the star you've got. From 60 solar masses to 100 solar masses, all the way at the very top of the HR diagram and the left of the main sequence, all the way down through the sun, and then the lowest mass stars in the universe, less than 1/10 of a solar mass down here at the very bottom of the main sequence. So this is a mass sequence. And in fact, if you've got a main sequence star, you can determine what its mass is pretty much just based on where it appears on this main sequence HR diagram. So mass is the most fundamental parameter of stars, really, overall. The mass of a normal hydrogen burning stars completely determines where it is on this diagram. The high mass stars being at the upper left, the low mass stars being at the lower right, luminosity and spectral type determined completely for main sequence stars by the mass of that object. Why is it that more massive stars are more luminous and hotter? Well, it has to do with the mass itself, right? The more mass a star has, the more that mass bears down on and crushes together and makes hot the very center of that star. And the hotter and denser and more pressure there is at the center of the star, the more efficient these nuclear reactions that are happening there happen. And therefore, the more luminous, the more energy they create, and the more luminous those stars actually are. So hotter core temperatures and higher densities and higher pressures leads to a higher nuclear fusion rate. And the higher the nuclear fusion rate is, the more luminous these stars will be. Okay, so we can use this information actually to give us a handle on how long we expect the star to live. We did this calculation for the homework last week, and you might remember that if you want to calculate how long something's going to last, this is the gas can problem. But first, let's think about what is the sun's life expectancy. We calculated that last week for homework. It is roughly 10 billion years. In other words, the sun, from the time it's formed until the time it runs out of hydrogen, we expect it to have enough fuel to last for 10 billion years. Now, we also know that calculating life expectancies is like the gas tank problem, right? The bigger the tank, the more fuel you have available, the longer you're going to last. But the faster you're using it up, the less long you're going to last. In fact, we can write this down. The main sequence lifetime of an object, of a star, let's say T sub ms for main sequence lifetime, is proportional to that object's mass divided by its luminosity. That is the gas can problem. The mass is how much fuel it has available. The bigger the mass, the more fuel it has available to it. The luminosity is how fast it's using it up. That's how fast it's generating energy and how fast it's radiating that energy away into space. So main sequence lifetime is proportional to mass divided by luminosity. Let's do some calculations then. Let's say a 10 solar mass star. How long do we think a 10 solar mass star is going to live? Well, we know it has 10 times more mass than the sun. But what is the luminosity of a star that is 10 times more massive than the sun? Well, we can go back and look, actually. here is a 10 solar mass star right here. It is 10,000, it's 10 to the 4 times more luminous than the sun. 10,000 times more luminous. So its luminosity is 10,000 times bigger than the luminosity of the sun. So the main sequence lifetime, again, if you do this just in terms of luminosity, in terms of proportionality constants, this is 10 divided by 10,000 times the sun. Since we're putting in how much more massive it is than the sun and how much more luminous it is than the sun. So 10 divided by 10,000 is 1/1000th that of the sun. And we know that the sun's main sequence lifetime is 10 billion years. We take 10 billion years and divide it by 1,000. This is 10 million years. We only expect a 10 solar mass star to live for about 10 million years. Now that sounds like a lot, but that's 1,000 times less long than we expect the sun to live. So this is a little bit counterintuitive. Our 10 solar mass star has 10 times as much fuel as the sun does, but it's using it up 10,000 times faster. And so its overall main sequence lifetime should be 1,000 times shorter. That's sort of the fate of these high mass stars. It's sort of analogous to high mass celebrities on Earth. Sometimes the brighter they shine, the faster they burn out. How about a low mass star? How about a 0.1 solar mass star? Well, we know that a 0.1 solar mass star has a luminosity that's about 0.01 the luminosity of the sun. So the main sequence lifetime proportional to the mass, which is 0.1, divided by the luminosity in solar units, which is 0.01 times the main sequence lifetime of the sun. Well, what's 0.1 divided by 0.01? Do it on your calculator. It's 10 times the main sequence lifetime of the sun. The main sequence lifetime of the sun is 10 billion years. So multiply 10 billion times 10, you get 100 billion years. The age, does anybody know what the age of the universe is? The age of the universe is only about 14 billion years old. There isn't a single 0.1 solar mass star that's been born in the universe that has yet come close to running out of hydrogen in the core. It will be 100 billion years and longer, actually, because of other complications with how these stars work, before any of them begin to run out of hydrogen in their cores. So the stellar mass is a very strong function of how long these stars will live on the main sequence. So here's a summary of main sequence stars. And this is just main sequence stars. Things get a little bit dicey once we get off the main sequence. But for main sequence stars, high mass stars have higher luminosities, they have larger radiuses, they have hotter surface temperatures, they look bluer in color, and they have larger radii than their low mass counterparts, which have much lower luminosity, are much smaller physically, are much longer lived, and are much cooler and therefore redder at their surface. Okay, we'll come back in the next class and talk about how it is that stars move off the main sequence and where they go and why that happens. So stay tuned.